we begin with analysis and classification of the interpenetrating nets. It should be noted that this procedure is available only for simplified compounds. So firstly, I should calculate the adjacency matrix and simplify the compound. If you do not know how to do it, take a look at our lessons, the AutoCM program, the standard simplification method, and special methods of simplification. So, I have first calculated the adjacency matrix for the compound. Let's simplify the compound by the standard method. I run ADS, Options, Save Simplified Net, Simplification Method Standard, Central Atoms, Metal. Then I have to delete all 0, 1, and 2 coordinated nodes, but there are no such nodes in the structure, so I may search for interpenetration. For this purpose, I use the classification option. ADS writes the information about interpenetrating nets in the output data. Ergo, ADS, Options, Default. This button sets the options which are necessary for the classification of the compound. Run. I choose all atoms as central. In the section Structure Group Analysis, you can see the composition of the framework, the number of the interpenetrated nets, the interpenetrating parameters. Here are FISE, PIC, PICVR, ZT, ZN, Z, and the class of the interpenetration. FISE is full interpenetration symmetry element. It is a single space group symmetry element that generates all Z equivalent interpenetrating nets. PIC is primitive interpenetration cell, that is, any cell that contains the same number of atoms for each individual net. PICVR is the ratio of the PIC volume divided by the primitive unit cell volume. ZD is the number of translationally equivalent interpenetrating nets. ZN is the number of non-translationally equivalent interpenetrating nets. The interpenetration belongs to class 2A. Z is the total number of the 3D interpenetration nets. Z equals Zn multiplied by Zd. The nets belong to the FFF topological type. You can find more information about the nomenclature for the interpenetration parameters in the ToposPro practical manual on the site topospro.com and in the corresponding articles. We can look at the structure and make sure that it has 2 interpenetrated nets. We can do the same analysis for molecular structure, bonded bivalent bonds. In this case, a simplification of the hydrogen-bonded net is needed. So, opening the Topology tab, I check the following options. The valence bonds connect atoms, the hydrogen bonds connect molecules. I click Whole Molecule in the Central Atoms window. Again, I should delete all 0 and 1 coordinated nodes and transform 2 coordinated nodes to the net edges. I run Compound, Auto-Determine, Simplify Adjacency Matrix, delete 0, 1, and 2 coordinated nodes. Now we have 2 3 coordinated nodes. ZA1 corresponds to the C9H3O3. ZA2 corresponds to the C12N2. I run ADS, Options, Default, Run to classify the net. As you can see, this structure consists of 18 interpenetrating nets, which are related by 4 partial interpenetrating vectors, PIV, and the non-translating interpenetration symmetry element, NISE. The class of the interpenetration is 3B. The nets have the SRS topological type. We can look at the structure and make sure that it consists of a large number of different nets. To paint a net with a non-standard color, you should select it. For this, you need to turn on this button and click on any atom. Then toggle to the magic wand tool and click on any atom of the selected net. In the magic wand window, you should toggle to the selected mode to apply the action to selected atoms only. Then open the change color window and select a color. Then you should click OK and unselect all atoms. Now you can see that there is a lot of different interpenetrating nets in the structure. Presently, I show you how to find the entanglements in the structure. You should simplify the structure before, because the large amount of the small rings slow down the calculation. As rings with size less than 8 atoms cannot be interpenetrated, I will delete them. I run ADS, Options, Simplify Adjacency Matrix, Simplification method skeleton, cluster rings from 0 to 8. We can look at the compound. As you can see, all small rings were transformed to the edges. Now I should delete all 0 and 1 coordinated nodes. Pay attention that you should keep 2 coordinated nodes, because in some structures they play an important role in the entanglement. I run compound, auto-determine, simplify adjacency matrix, delete 0 and 1 coordinated nodes. Now I can look for the entanglement. Ergo, I apply ADS, Options, Common. Here I am checking the option Write Data to TNT. This option saves a TNT file which allows you to visualize the rings in the structure. In the Topology tab, you should check the option Entanglement. If maximum ring is 0, ADS will not distinguish cycles and rings, so it will look for entanglement between cycles. If we set maximum ring option, ADS determines if there was a cycle ring or not, so it looks for the entanglement between rings. When you specify maximum ring size, it is better to set the maximum ring equal to 10, 12, because it is enough for the most number of structures. You should remember, the larger the maximum ring is, the slower calculation will be. If we set option maximum ring sum, ADS will look for the entanglement between strong rings. You can find more information about entanglements in our webinar Entanglements in Coordination Polymers, Analysis and Classification by Topological Methods, and in the corresponding articles. So I choose maximum ring equal to 12 and run ADS. The central atoms are all atoms. Here you can see which bonds cross the rings. This is the summary table of all types of the rings crossings. We see that rings are not linked together. The shortest chain between them is infinite. The rings 18A and 24A form a non-Hopf link. Each ring crosses another ring at one time, and the rings are not linked. Each ring is crossed by 4 other rings. Let's look at the rings. I click Image, Rings, expand the tree, and grow the structure several times to get the records in bold. Then I select the rings and click the Apply button. Now you see the interpenetrating rings. This is a non-Hopf ring link. We can join these rings. This is a Hopf ring link. The rings are connected with each other. We can recolor these rings by the magic wand. And change the view of the structure. Now you can see the entanglement part of the structure more clearly. You should construct the Hopf ring net and determine its topology to classify the entanglements. This is the net the nodes and edges of which correspond to the rings and Hopf links between them. The Hopf ring net characterizes directly the catenation pattern. So I run ADS, Options, Save Simplified Net, Simplification Method Ring Net. In the Topology tab, I check the Entanglement option and set the maximum ring value equal to 12. We have a new database with a simplified crystal structure. As you can see, the structure has pseudocarbon atoms, bonded by valence and hydrogen bonds. The carbon atoms coincide with the centers of rings. Valence bonds correspond to the edges shared by rings. Hydrogen bonds correspond to the Hopf links. Let's look at the structure. Here we can see the net, the nodes and edges of which correspond to rings and Hopf links between them. Let's determine the topology of the Hopf ring net. I run ADS, Options, Topology, Classification, Valence bonds none, Hydrogen bonds connect atoms. As you can see, the Hopf ring net has the SQL topology. I have used the skeleton simplification method for the compound. Generally, you can also use the standard or cluster methods. In most cases, all methods give the same result. That is, the topology of Hopf ring net will be the same. Besides, if clusters take part in the interpenetration, different simplification methods will give different Hopf ring nets. These structures require a more detailed analysis. So, if you analyze one or several structures, we recommend you to use the skeleton simplification method. If you analyze a large amount of structures, we recommend you to use the cluster simplification method, because in this case calculations will be faster. If you cannot simplify the structure by the cluster simplification, you should use the standard simplification. Finally, I should determine the topology of the entangled nets. For this purpose, I should first simplify the structure. I may use the cluster or standard simplification. I run ADS, Options, Save Simplify Net, Simplification Method Standard. I choose metal atoms as central. Before classification, I should delete all 0 and 1 coordinated nodes and transform 2 coordinated nodes to edges. Otherwise, the classification will be wrong, but there are no such nodes in the structure. Now I can classify the net. I run ADS, Options, Default. As you can see, the net has the PDS topology. Also, I may do the cluster simplification. I run ADS, Option, Save Simplified Net, Simplification Method, Cluster. Now I should make the standard simplification for the molecular packing, connected by hydrogen bonds. You can find a more detailed information about the cluster simplification in our lesson Special Methods of Simplification. Again, I should delete all 0 and 1 coordinated nodes and transform 2 coordinated nodes to edges. I run Compound, Auto-determine, Simplify Adjacency Matrix, delete 0, 1 and 2 coordinated nodes. Now I can classify the net. I run ADS, Options, Default. As you can see in this representation, the net has the TFI topology. Now let's consider the structure with Poly Catenation. At the first stage, I should delete all small rings from the structure. So I apply ADS, Options, Save Simplified Net, Simplification Method Skeleton, clustering from 0 to 8. Now I should delete all 0 and 1 coordinated nodes. Pay attention that you should keep 2 coordinated nodes because in some structures they play an important role for the entanglement. Now I can search for Poly Catenation. I run ADS, Options, Default, Topology tab Entanglement, maximum ring 12. ADS informs you that there is a Poly Catenation 2D plus 2D between 2 planes with angle 62.7. So the Poly Catenation is inclined, not parallel. Pay attention that ADS does not recognize Poly Catenation and low-dimensional interpenetration. In former case, the resulting extended array of entanglement nets has a higher dimensionality than each of the nets. In the latter case, the dimensionalities coincide. At the same time, the inclined entanglement is always a Poly Catenation. You can find more detailed information about Poly Catenation in the corresponding article. Let us draw the structure to look at the Poly Catenation. Ergo, we have considered the main ToposPro functions, which are very useful for searching for and analyzing of the entanglements. For more detailed information about possibilities of the program package ToposPro, you may address to our lessons and webinars on our website topospro.com.